The right hand rule for the induced current from a magnetic field uses the magnetic field coming from a magnet in this case and the area vector. So these two scenarios are actually the same, but they have different area vectors, both of which are equal to the area inside of the wire loop that's next to the magnet. The magnetic field is pointing away from the magnet, and it's decreasing as it gets further away. So you have to find the flux of each of these, but first you have to determine which way your area vector is going to be pointing. So in this one, we said that the area vector is pointing to the right, and in this one, we said that the area vector is pointing to the left. So then you can set up this table, which uses the magnetic field pointing the same direction for both, the area vector pointing in opposite directions. So when you do that, you get that the flux here for the first scenario is going to be positive at first, and the velocity says it's moving this way away from the magnet, which means that the final magnetic flux is going to be lower than the initial. So then to find d flux over dt, you subtract the final minus the initial, get a negative number. V individual is positive, and so then you use the right hand rule, point your thumb in the direction of dA because it's positive, and then the way that your fingers curl is the way that the induced current is moving. So in this scenario, it'd be moving in that direction. For the other one, same magnetic field, opposite dA pointing in the opposite direction. The initial flux is a big negative number, final flux is little negative, so the change is positive. V individual would be, or induced would be negative, meaning that you would point your thumb in the opposite direction of dA. dA is in this direction, so you point the opposite direction. The way that your fingers curl gives you that direction of current, which is the same as the other one, so that makes sense.